So, so in software engineering, we tend to kind of abuse these terms or overuse these terms like libraries, frameworks, runtimes, engines, utilities, factories, things like that. But in the JavaScript context, things are a little more defined, at least around the engine and runtime and framework and library. So according to me, library is something that gives a piece of functionality, but is not opinionated about how you're going to use it, right? It doesn't take over the control. It just gives you a bunch of utilities, and then you can decide how you want to work with it, like jQuery or Express, TanStack query, React. Yeah, I know that could get you in hot soup, but React, according to me, is a library. But then you have frameworks. So frameworks basically take over the flow of the program, and usually they are like a inversion of control kind of containers that's there. So you have Next.js, Angular, Ember, or Nest.js. They could all be considered frameworks. And then finally, you have the runtime. Runtime is basically where it provides the scaffold for JavaScript to execute. So the most popular one is, of course, the browser. So every time you open up a browser and you type in a URL, you're actually using a runtime, which is the browser. About 14 years ago, Ryan Dahl created Node.js, which was basically he took the Chrome's V8 engine and he built a scaffold around it, and so that you could run it on the server, and then he had this whole eventing mechanism around it, and so on and so forth, and that kind of gave rise to server-side JavaScript. There's Node and Dino and Bun there. There's Cloudflare Workers. There's also React Native, which is a very interesting runtime actually that's there. And then you have the actual engines. That's where JavaScript code really gets parsed and converted to machine code and executed and all that. That happens in the engine. So you have V8, which is basically used by every single big browser now. I mean, like from Chrome, Brave, Internet Explorer, everybody uses V8. There's also SpiderMonkey by Firefox, Mozilla kind of browsers, and then there's JavaScript Core, which runs in Safari, and Bun is actually built on JavaScript Core, and then Hermes is by Meta, and that's what is powering React Native. And the thing about Hermes is that it doesn't have a JIT compiler, and the reason that was important is because iOS does not allow JIT compilation for any of their apps. So they needed to have a JavaScript runtime that would work well, and so Hermes has the design it has, and it powers React Native. And then there's also QuickJS, which is an amazing runtime. It's written in C. It's very small that it can even run on microcontrollers and things like that. So that's QuickJS. So here we are going to squarely focus on the runtime, and we're going to focus on the Rust aspects of the runtime. So what are the responsibilities that a runtime should do, right? I mean, so one of the first things it should do is it should provide an integration and a little bit of, and give the right abstractions on top of the engine, right? For example, here we are talking about V8. So V8 has this mechanism for isolates and context. So it needs to create those types and the abstractions which will allow us to talk to those isolates and contexts and so on and so forth. It needs to implement the event loop. So in the browser, event loop is basically everything that you do with the mouse clicks and things like that. But on the server side, you could have fetch, or you could have timers, you can have processes, all different kinds of IOs. So you need to implement the event loop. And then optionally, it would be nice if all runtimes implement the WinterTC or the WinterCG. This thing is Web Interoperability Common Group. It's now actually become like a technical spec, so it's WinterTC now. So it gives us the web's standard IDL. It has URL, timers, fetch, request, response, crypto. All of that is a part of the WinterCG spec. So if a runtime implements that, it'll be good. Like Dino implements it. Cloudflare more or less does that. Vercel Edge runtime is also getting there, so on and so forth. And then it needs to support module loading. So JavaScript is an old language, so you have the script and the compilation, but then they added the ES modules. So ES modules are handled a little differently, and then you also have nuances around like the standard imports versus dynamic imports and all that. So you need a way to set up this module loading system. And TypeScript has become so popular that pretty much every single runtime these days actually supports TypeScript natively. So you need to have transpilation support, so that when you just say node or dno and then just point it to a TypeScript file and people expect it to work. So that's the next thing. And finally, you can decide what to support in terms of your environment. And say, oh, do you want to support network access and opening up ports and accepting socket connections and things like that, or do you want to support file access, process, environment, sockets, all of that stuff. So you can decide what you want to support as a part of the rest of the environment. So that all makes up the runtime. So this is my open source toy JavaScript runtime that I wrote for this talk. So basically, it has the V8 integration in Rust. It has basic ES module support. It has a sort of like a very laughable event loop implementation. It gets the idea right, but then there's so many like sharp edges in there. But it kind of like exercises the idea that you have a message pump and you access those messages and go through that. I have a couple of synchronous Rust callback examples like print and add, where it's just synchronous methods that you can call. And then I have a few async implementations that exercises the event loop as a part of that. And I also have some notes to go along with it. So that's in v8notes.wagme.ca. That's there. Okay, so the minimal thing that you need for, I know this is a lot of code, we'll dig deep into it, but the idea is that this is all it takes to actually call out to V8 and execute your program. I mean, even though it looks like a lot of lines, it's actually fairly straightforward, and we'll dig deeper into this. And this is like a fully compilable Rust program, so you don't need imports. This is like, I tried to cram everything into just like one main function as possible, and this works. So what it starts with is initializing the V8 engine. So this basically sets up, and you do this once per process. So you set up the platform, you initialize the platform, and then you initialize V8 itself, right? Which is the engine. So this basically sets up the core thread loop that the V8 itself has for parsing and things like that. It sets up its memory structures, it sets up the outer garbage collector and so on and so forth, and initializes the platform. And this happens once per process. After this is done, you set up V8. We then create an isolate. So isolate is like an island in this. It has its own heap as a part of the execution, and you can also do as a part of create params. You can do memory limits or heap limits on it, and so on and so forth. So conceptually, this is what an isolate looks like. It primarily isolates the heap to make sure that no two isolates share the same memory, actually. It has a garbage collector associated with the heap, so that if you have a generational garbage collector, you have the new and the old variants, and depending on the number of generations that are there. And then when you get the code, that goes through the execution pipeline, and the execution pipeline is like you parse the JavaScript code, you then go through the slow interpreted process, which is the ignition engine, which is fast to start up, but then slow execution. And then finally, the JIT kicks in, and that's when turbofan comes up, and then it actually compiles it down to native code. So you have all that as also in the heap. And then when the code executes, of course, you have the execution stack, and then the threads to make sure that this particular execution or context holds on to this thread, because you could have multiple contexts on the same isolate, multiple tabs could share the same thing. And then you also have microtask queue for promises. So for example, if you do async await on something, and then an await finishes, then it basically has to change the task, the call graph to do this. So those are tracked in the microtask queue, and so those are handled. And that is also exposed to the Rust world, actually. So if you have a callback that kind of resolves on a promise, supposedly, then you can actually increment the microtask pointer. And finally, you have the Rust side of things with the handle scopes. So a handle scope is basically a handle to the C++ world, because in C++ world you have the heap and the garbage collector, so the memory could move like on the C++ side, but the Rust side needs to keep track of where this memory is so that it needs to handle all these things. So handle scope is basically like a handle to the C++ scopes. When they change, then like Rust is informed about where these changes happen. So once the isolate, so this is how you set up the isolate, where you have the isolate here and you have the, you create it. And after the isolate is created, you create a handle scope to the isolate, so which is basically a bunch of handles to the heap that is there. And you have to initialize that. And once you initialize that, you also have to create a context. Now the context, like you can have, isolate is single threaded, so that means that every isolate needs to be run on a single thread. You cannot move the isolate around to different threads. It is not safe. So since it is pinned to a single thread, if you have to run multiple executions of something, you need to set up multiple contexts for it. Like for example, let me go on and then come back here. For a context, it's like a dormant sandbox for JS objects. So for example, every time you do an array or an object or math object and all that, they're all hosted on globals, and the JavaScript code can actually change the prototype on it. Right? So when you execute a JavaScript code, it can actually go and change the prototype. So if you run multiple executions of it, then there is no guarantee that okay, this particular implementation could change the global of it and it could kind of blow up somewhere else. So this is what the context does. So the context essentially isolates these globals that are there, and they provide their own set of globals, but it's all shared all in the same heap though. So the heap for multiple contexts would be shared in the same isolate, and you can only have one context executing at a time in the heap. So that's how it is. So that's for the context. And the way you use a context is that you enter a context and you execute code against a context and you leave. And that's where the thread locker is. So this is the thread locker for the context. So when you execute a context, it acquires a lock on the thread for the isolate, and it releases it after the execution is done. So that's the context scope. So you have the isolate, you have the handle to the isolate, you have a context. You can have multiple contexts per an isolate, and then you have the scope for the context. So hope this hierarchy is clear. So that's how this is set up. So once you have all of the scope and these contexts set up, then you can go ahead and execute code. So let's look at this code. So how do we execute this code? So let's say we have a templated string here, and it says the answer is 6 times 7, 6, 7, it's 42. Yeah. So I mean, I had to make that obligatory joke there. It's 6, 42. So and then you have to first convert that string, which is a UTF-8 string in Rust, to a V8 string, which is UTF-16 actually. So you convert that to construct V8 string new based on that. And I have unwraps. Sorry, I have a typo on the unwrap here. But you have all of these unwraps here because they all give options back. So you get the code, and then you compile the code, and then you get the script. And this is basically where you get any parsing errors or things like that with JavaScript. If you make typos, that's where this gets caught. So if you get a none here, and then you can find that out. And then you basically then run the script actually to get the value. And here, since it's just a evaluation that is run on the string, so you would get back a V8 value. So V8 value is sort of like a catch-all type for all of V8 objects. And then you have to specialize that V8 value to a particular V8 specific value, like for example a V8 string here to do this. And then finally you have to convert it to a Rust string. So and this is the expensive bit. So the most expensive bit is actually converting from V8 types to the Rust types. So as much as you can keep your execution on the V8 side the same, and then kind of deal with array buffers or things like that there, you could have really performant V8 engines. But if you have to swap in types in and out, of Rust that becomes slow, actually. But it's not too bad. I mean, in the large scheme of things, it's not bad. But this is basically, I mean, like if it's like performance tuning for V8 and this thing, like this is where the first thing I'd look into and figure out, okay, where are these things crossing boundaries, and then minimize that. So this is for execution. So hopefully it's clear from this point. Okay, cool. Now we'll dig a little deeper. Let's try to create a Rust function that we can call from JavaScript, right? So we essentially need a callback in the Rust so that this gets called. So what we're going to do is like have a very simple function that's just going to add 2 numbers, right? So to do that, this is the signature for every single JavaScript Rust function that you would write that needs to be called to JavaScript. So you will have the first argument is a scope, and this is the context scope that we set up, right? So we set up the context and we set the context scope. So the first argument will be a context scope or a scope derived from the context scope, and then you will have the arguments to the functions, and then finally a return value. And here the return value, if you see, it's a mutable return value, and this is like the old school C kind of like return values that you do, right? Where you say, oh, you get the pointer to a mutable value and then you return and essentially treat it as the return value. So you get that, and essentially you get the args.getZero of this and args.getZero of that, and you get the number value of it. And at this point in time, these are JavaScript numbers, essentially floats. Right, so and if that doesn't exist, because the infuriating part about JavaScript is that a function could take 2 or 3 arguments, but you can pass it how many ever arguments you want. It's totally valid. So you always need to check if the even if you have an actual JavaScript function, you are getting all those arguments into this. So you don't get any help from the compiler or the V8 interpreter whatsoever. So you have to basically get those values in there. And then finally, on the retval, we set the value. So where we just add these 2 numbers, a plus b, and then we create a new V8 number out of this, and we set it into the return value. So we have a callback in the Rust code now. Now let's see how do you add it to the scope. So we have a create add method here. So we have our friendly context scope that comes up here again. So from the context scope, we can access the global object. So this is the global this associated with the context. So I told you that each context has different global this. So you get the global this for that particular context, and then you basically create a string. This is the name with which we want to hoist our add method. We call it underscore underscore. I mean, it's like a convention. There's no rule. So the convention is that anything that is like underneath in the Rust layer or C++ layer, you have like underscore underscore or things like that, and then you hoist them up. And then you create the function out of this. You create a function template, and then you create the V8 function pointer to that. And then in the global object, you basically set the name to the function pointer and associate them. And that's pretty straightforward. And once that is there, you can then call it. So here we create the context scope like how we created earlier. We create the add method and then send it the context scope, and then we can then use this as a part of the answer here. The answer is underscore underscore add 16 and 26, which should still be 42, and then we basically can create the code object and compile it and execute it the same way that we did the last time. So this is for doing the add method. A deep breath and some water. All right, so far we got how we do the script compilation. We got how we did hoisting the Rust methods into JavaScript to call it, and now we have to talk about async methods. So async methods, how does it work? It has this concept of the event loop. So JavaScript by itself is not async friendly. It runs in a tight loop. There is no async support itself in JavaScript. It has to come from the runtime. The engine itself doesn't support it. So the way it works is that when you call something like a set timeout, we create an ID. So the set timeout actually has 2 parameters, right? One is the callback method and the timeout for this, actually. So when we get this call for set timeout, we'll get to the native timeout method that's there, But before this, in JavaScript, we can actually say, hey, the set timeout is a call which will create a new ID. This is all done in the context global scope. We create an ID and then we associate this callback with that particular ID. It's basically like a hash map, like an object which says, oh, ID plus plus ID1 for this callback is basically this callback function. And then we call the actual native timeout method. The native timeout method is simply Tokyo sleep loop. So this will basically schedule message. So it'll call the scheduler and then say, hey, I'm going to send this message called scheduler message of schedule timeout, and it'll give the ID and the delay, right? So that we have. And all that does is like, it returns a future. It returns a future. It says Tokyo spawn, and then it'll basically do this. So now this future is spawned actually, and once this future is spawned, this will send a callback message to say that, hey, I have executed the timeout. It's done. So it's the runtime's job to pump the callback. So it's called the pumping the message loop. So it will pump the callback, and when this process message is called every tick. In the ToyJS code base, we are basically sleeping every 100 milliseconds and say process callback again. Process callback. Process. It's like a very naive way of doing it, but it works, right? So in Node.js and things like that, this process callback actually does a lot more, where it keeps an inventory of all the callback items that are there, and it's not that naive, but more or less the idea is the same. So it runs in the same thread as the one that's holding the isolate. So the process callback needs to run on the same thread, and every time it runs, it basically yields the execution back for some time to this thing, and the time to which it yields the execution could be 16 milliseconds, 20 milliseconds, 5 milliseconds. It doesn't matter what it is. In my case, I just chose 100 milliseconds to do that. So this is how the event loop works. So let me show this real quick as a demo, and then I'll come back. So I have this file which is index.js, and I have a math.js as well here, which does this. But this is pretty straightforward. It just adds two numbers. I have a print method here, which is a Rust method that I wrote, which is hosted onto the ToyJS code. And I also have a fetch call, which just gets the IP address that's there, and it shows the JSON content. And then I also have set timeout. So it has top level async awaits, it has ES modules, it has timers, all of the interesting things that could go wrong with a JavaScript runtime. So I'm basically going to execute this ToyJS function, and when I do this, let's walk through some of the trace. So once the execution starts, it starts an event loop, and then it looks to compile the module index.js. And then it compiles the module, and then it instantiates the module. And when it instantiates the module, it sees that, hey, I need to load math.js here. So the module resolver is called, it gets the /math.js, which is the specifier for the module. It says the referring module has this hash. It just calculates the hash based on the content of the module. And then it says this is the referrer path, and this is the resolved path. And I want to load the module from the file. So if the same module is loaded again, I maintain like a cache which does this. It's like a very simple hash map. I haven't implemented like an LRU cache or something like that. But typically in a real runtime, you want to implement an LRU cache so that you keep that active. So this is just a hash map which just loads that. And once it instantiates that module, it starts evaluating this particular module. And that's where this particular line is called. So even though this module is called, this particular line is red, it does this. It actually does the resolution callback, and it actually calls all the other modules, and then it evaluates this module, right? The main module. This line only starts after all the other modules have already run, actually. So it starts from here, and then once it does that, it prints that line, and then it starts the fetch. And when it does this fetch, I actually generate an ID for fetch, and I say this is the ID and this is the URL for the fetch message, and it returns an object back, and it basically calls the fetch success. And when fetch success calls, it basically resolves this the await, the left side of await basically becomes the callback, because that's how promises work. You have the resolve and the reject. So this is basically just syntactic sugar over resolve and reject. So it's going to call the resolve callback. So the resolve callback then calls the rest JSON, and then it actually prints the stringified content here. That's here. And then the same thing happens for timeout. So you call the timeout, I create another ID for the timeout, I set the delay for this, and then it executes the delay call. Right? So each one of them basically has different like modules and callbacks, and they kind of work together. So this is a very naive example. So I'm going to show one more example of how it's used in our product. So we do things a little bit more interesting. So this is our product. So we have two things. One is for Urai voice, and like we have the bigger agentic pipeline. But for voice, it's used for simple, straightforward, sort of like native voice interaction. So what I'm going to do is I'm going to send a message to a number that I have. Let's see. So I'm basically saying I want to make a reservation for 5 people for a birthday party. So let's see how this works. See if this. So I should get a call back.
Hello, this is the Uri Bistro concierge calling about your reservation. Is this a good time to speak?
Yeah.
Great. I'm calling to confirm a reservation for a birthday party for 5 people. Could you please confirm your full name for me?
Yeah, my name is Bagmi, B-A-G-M-I.
Thank you, Bagmi. And what date and time were you thinking for the reservation?
Maybe tomorrow at 5 p.m.
And will this be in the general dining area or a private hall?
Just a general dining area should be fine.
Great. And for a birthday party, are there any special requests or allergies we should know about?
Just some vegetarian options would be good.
Perfect. And what's the name of the company, if applicable?
No company, it's just a private party.
Got it. Just to confirm, the reservation is for 5 people tomorrow at 5 p.m. in the general dining area with vegetarian options requested.
That's good.
Is that all correct?
Yep.
Is there anything else I can help you with?
No, that would be all.
Great. I'll send you a confirmation SMS now. Thank you for calling Uri Bistro.
All right.
Bye.
Thank you. Hi, by the way, can I also talk to a human there? Okay, I got it. I said bye. No, I got this. So here, if you see here, as a part of the agent thread, it did a bunch of things. It actually created a reservation for the name, and then it called. Sorry, I'm just going to increase the font size. I just realized it might be too small. So it creates a reservation, and then it calls the SMS with the body, and then it does the hang up as well. And all these are, it comes with a very, very simple agent instruction where I have all these things, but I have these tools that are associated with it. I just ask it to collect some data and so on and so forth, and then ask it to call the tools. And these tools are very, very simple scripts. Like for example, this is the one which does reservation into Superbase. Like for example, it should have inserted it. Like for example, this is the call that we did right now, and it basically took this data and inserted it into the Superbase table. And essentially, the advantage of writing a JS runtime and running it yourself is, if I can get to here. Yes, I'm sorry. If you can get to this. So this is the script that actually does the Superbase reservations. So as you can see here, I do the ES module loading from like a HTTP URL, just like how Deno supports it. I also have the JS doc comments on top of the Superbase reservation for the tool. These are, and I also support like the ES7 decorator syntax on top for these tools, so that it gets reflected on that, and it basically does the tool registration automatically for this registration. And then I also parse all these JSTalk comments with treesitter, and I also generate a schema JSON based on that. This is basically what gets sent to LLM for the tool call specification and so on and so forth. So that actually is done there. And so it makes it really simple for us to extend this system. So since it's like a since we control the runtime for the underlying system, it makes it easy for us to extend this. So in fact, even the call transfer or the hang up and all of that kind of things are also implemented as commands into this system, and so this doesn't even it runs in the same process as my agent loop executor actually. So one other thing that I wanted to show is that here you have the secrets that get injected, that's there. So, and this is also done per execution and per call. So it would have been a little difficult to do this if it were like two different systems. Your, if you host it on say Cloudflare Workers or something like that, that will have its own like API keys and so on and so forth. And managing execution context for the same tool for two different customers and two different clients with two different accounts, all that becomes very difficult if you have to manage multiple deployments like that and coordinate different missions. And that's the reason why we chose to essentially bite the bullet and build our own runtime and make this platform extensible. So that's that. But that said, I wanted to talk a little bit more. I think we are going ahead of time. So let me talk a little bit about the module loading. I was like, I don't know, maybe if I'll have time to talk about it, because when I was rehearsing, I guess we did this. So typically in a module loading scenario, you have the main module, and then you have the sub-modules that get loaded. Like for example, if you have a server.js, that could load models.js, controllers.js, services.js. But then both models and controllers.js could use utils.js, right? So it's basically like a directed acyclic graph of dependencies that are there. And whenever you use these models, you essentially have to, first compile the model that's there. So since this was like an add-on, so we looked at the V8 script compile, but then we also have the V8 script compiler that's independent of the V8 scripts actually, and it was very confusing when I first got my head around this. It's just the module compilation and the module loading actually takes a very different code path from the normal script compilation, and so much so that even the types for them are different. So in the module compilation case, you basically still have the standard context scope, but then you create a new derived scope from the context scope that's there, and you try to load everything into that derived scope, because this resolution happens at the loading time for the first time it's executed. So you create an isolate, you create a context, and then you create like a module loading context for this, and then you load all the modules via the module loading scope, and then you create you load these modules via that scope. So this is the try-catch scope that's there. So from the try-catch scope, you basically load the string that is for the code. You try to set up a script origin for that scope. So script origin is like, hey, what's the file name? You could also it also supports like bundled configurations. So you could also do things like from a starting line, from this column number, it starts from here, sort of thing. And then you can give a script ID. You can even load like WASM modules as a part of this, and then you can also do things like source maps and do this. So it actually is pretty extensive as a part of the script origin. And once you have the script origin, you create a source object. And again, this is a part of the V8 script compiler's source object. You create a source object with the source string and the origin that's specified with it. And then you compile the module. This is the initial compilation. And then you create the module. And when you create the module, since this is like a graph of this structure like this, you also give it a visitor. So it's like a tree visitor or a graph visitor pattern. So you give it a visitor called the module resolver visitor. So the module resolver basically takes the current context, it takes a given specifier, and then it gives the reference module and tries to load the new module. So it basically is going to visit that for every node in the graph with the module resolver. And module resolver is the place where you could do caching and loading from caching, right? So like if you go to the module resolver, it's going to call it for every node, regardless of whether it has already seen it or not. So if you are going to visit utils.js twice, basically it's the module resolver's loader implementation that you can do this. So I have an FS loader, which is a file system loader, and that actually does that. So you could have different loaders. So like if for my visiting from that URLs, I did a URL loader that's there, and so on and so forth. So you could have different loaders, and then depending on the referrer type, you can actually go to a different loader and then load and have your own cache based on that. And yeah, that's my talk. We are a little ahead of time, but I'd be very happy to take any questions that you have. And also, please give me your feedback. It'll be really helpful in preparing for the next talks and things like that. Yes, please.
Can you talk a little bit more about why you need your own runtime for the project that you're building?
Yes. I mentioned about the call handling scripts and so on and so forth as a part of this. So, like for example, here as a part of the call, we also do transfers and hangups and things like that, and all of that is handled through call handling actually, and they are simply commands that we send down. So we want the environment to be programmable. So for example, if the agent decides to say, oh, I want to route this call to another expert, which has its own context and so on and so forth, and I need to be able to pass this information on and so on and so forth. We don't want to leave the context of the call that's there. So we want to keep these streams of UDP packets that are flowing media packets alive, and we want to have as minimal a latency as possible to do that switching logic and so on and so forth. So and that's the reason we wanted to basically have the engine embedded along with the with the runtime, the place where the call handling is happening and so on. Yes. Yes.
How does dynamic input work?
That's a really good point. In my ToyJS it doesn't work, but I actually just did the binding for it. So here when we create the runtime, just give me one moment. I have the setup bindings here, and in the setup bindings, so let me here. So yeah. So this is done as a part of the binding. So in the runtime, when we create the runtime, okay, sorry. Let me close this. Yeah. So in the isolate, you can actually set host import module dynamically callback, and this is the callback that's get called. And in this callback, basically this is the dynamic import. And right now I'm basically saying that no, I'm not giving a dynamic callback here, but essentially it needs to return a promise, and that promise should resolve to a module basically. Right? So as long as the promise resolves to a module, then you can do dynamic code. It was just too much code and too much work for dynamic imports, so my runtime currently doesn't support dynamic imports.
The dynamic import module compiled when the referees compile, or is it compiled at runtime?
No, it is compiled at runtime. It's not. Yeah, that's one of the other things with that is that it includes that code path there for compilation that's outside your typical. Yeah. Yes. So, yeah.
Typically, you're able to define extra functions for the JavaScript handle. I would imagine as a JS developer, if I were to try and define my own function, I would use like add, which is a common name. I would also consider prefixing it with double underscore to make sure it doesn't conflict with something from the spec.
Yeah.
But then it would conflict with yours.
That's correct.
Is there a message that you can tell V8 to send when you try and override the existing definition and say, actually, this runtime did provide that function?
That is a good question. So I don't know the answer to that. I'll need to look into it if there's a hook which can do that. Yeah, but that's a good point. Maybe I mean one way to do it is like doing underscore toy underscore or something like that, or underscore Dino or something. Yeah. Yeah. Name or namespaces. Yeah.
But any name that you choose could conflict. So
Yeah.
Yes.
Yes.
Global giant.
Exactly. Yeah. Good. Yeah. Yes.
Yeah, just out of curiosity, how much time did it took you to build that JavaScript runtime in Rust?
It took roughly about I started last Confoo, and then it took me about 8 months to do that. The ToyJS though, it was easy for me because I was extracting it out from the